just going to give us a different way of looking at some of the content we've seen so far this chapter about choice. And so we want to represent preferences by this utility function, by u of x1, x2, for instance. We know that the marginal rate of substitution at x1, x2 is equal to this price ratio. Now, you forget the negative sign, but that negative sign, we should make sure it's in there. Well, we know that the MRS can be represented by the ratio of marginal utilities. And it's really by the negative ratio of marginal utilities. I'll put negative in brackets, like it's the negative ratio, right? And so essentially what we have is the derivative of our utility function, the partial with respect to x1, over the partial of our utility function with respect to x2 equals this price ratio. And so what I'm doing here is I'm just dropping, the MRS is the negative version of this, and it equals the negative price ratio. I'm just dropping that -1, or I'm multiplying both sides by -1 here. So we know this must be true. And we know it must also, the solution, the x1 and x2 that does this, must also satisfy the budget constraint. P1 x1 plus P2 x2 equals m. So all this means is we have two equations and two unknowns. And so we can solve for that. So let's quickly erase this and we'll solve for that, and then we'll talk about a more systematic way, or a couple more systematic ways to kind of solve for these. Partial of the utility function with respect to x1 over the partial of the utility function with respect to x2, and that equals the price ratio. And then we have the second one, which is our budget constraint, which is P1 x1 plus P2 x2 equals m. So let's rearrange two. In order to write x1 as a function of the rest, right? Or x2 as a function of the rest, maybe. So we're going to rearrange this second equation to get x2 equals something. And if we rearrange that into the algebra, we're going to have P2 x2 equals m minus P1 x1. Just moving this side over. Then you divide both sides by P2, so x2 is alone. So this is the equation we get. And what we want to do is sub this into 1, to this part. And so essentially, this is when putting those little dots is maybe hopefully not too confusing. I'm going to write it out again. So derivative of u, which is a function of x1, and then instead of x2 in these brackets, we're going to write this whole expression here. M over P2, I should say, minus P1 x1 over P2. So the derivative of that, partial with respect to x1. And then the partial of that same utility function written as a function of x1, and then x2 written as a function of x1. Which is essentially what we're doing here. That with respect to x2, and that equals that price ratio. So we're basically rearranging this and kind of sticking it in this first one. And that's kind of then we have two equations and two unknowns, and we could solve this. Now, we can do this in a more systematic way. using calculus. Using calculus, and I'll say conditions for finding a maximum. For finding a maximum. So let's take a look at kind of two different ways of doing a very similar thing. Here we're just using two equations. So the partial, the MRS being equal to, or the negative of the MRS being equal to the negative of the price ratio, or the negative of the MRS equal to the price ratio. And the second one is the budget constraint. And we can rearrange this budget constraint, plug it into this condition, and we could solve for it. But we can also kind of use these ideas of maximization. We could kind of transform this into an unconstrained maximization problem, or we can use a Lagrangian and kind of look at a constrained maximization problem and solve it that way. So let's look at those two methods, and then we'll do an example with kind of Cobb-Douglas. Kind of come back to that Cobb-Douglas example and kind of derive those demand functions.